good. Okay, we're back after the coffee break. Lecture 8, non-holonomic constraints. We talked before the break a lot about the type of constraint. Now we want to derive the equations of motion with non-holonomic constraints. So deriving equation of motion for a non-holonomic constraint system. And yeah, it sounds maybe boring, but of course we start again with the virtual power of the applied forces at the center of mass plus the D'Alembert forces, and the plus is of course a minus sign for the D'Alembert forces. And so this is the virtual power, and that should be 0, yeah, for all virtual velocities which fulfill the constraints. Fulfill the constraints. Okay, and what are the constraints? Then, if that's the case, then the system, it's a statement, is in dynamic equilibrium. That is a statement. Now our non-holonomic constraints can in generality be written like Sk being some pseudo Jacobian, it's just a training matrix. Ski times x dot I is 0, where we have k non-holonomic constraints. For now I just focus on the non-holonomic constraints. We know how to do regular constraints, so let's only take non-holonomic constraints. The complex case is of course in the book, the complete one, but for now let's focus on this. Now this is for the real velocities, and as I said, virtual velocities, you put a v there, a hat or some magic symbol, and for some reason people like this curly delta as a magic symbol. So virtual velocities, then we get delta sk is ski delta x dot I, should be 0. So these are our virtual non-holonomic constraints. Then we're going to put them again into this equation by means of the famous Lagrangian multipliers, the unknown Lagrangian multipliers. So delta p star, it's now a different thing. Again, the original part which we had, x double dot I, delta x dot I minus lambda k, and the minus or plus is just a sign convention. I tend to like minus, but because then everything is on one side of the equation. But as you like it, it's like Shakespeare, as you like it. So that should be 0, and now this holds for all virtual velocities, for which we can write that this delta sk is this ski delta x dot E. Okay, and of course the delta sk should not all be 0, right? Okay, putting that into equation, then we can express everything in terms of the virtual velocities of the center of mass. So we get delta p star, and then we can put everything under the bracket, mij x double dot j minus this lambda k, oh, I was a bit too quick, ski and delta x dot I is 0. And now this holds of course for all virtual velocities as long as they're not 0. Since this must hold for all non-zero virtual velocities, then we get in total I equations, right? So we get I equations of motion, being motions. Fi minus mij x double dot j minus lambda k ski is 0. And of course, we have to trail along our glue, right? Now we have a different type of glue. First we had holonomic glue. Now we have this rapid non-holonomic glue. Different type, but still glue is glue. So that was on the velocities, our constraint, but now we need it on the velocities. So we need we take this one as ki x dot I is 0, and then we differentiate with time. So we get xki x double dot I plus ski comma j x dot I x dot j is 0. Now these two set of equations, we can write them in this pseudo matrix vector index notation form, which is sort of clarifying everything. So we have this mij, we have the not a Jacobian, it's just a linear mapping because the constraints are linear in the velocities. By the way, I have never seen a rolling or a contact problem where the constraints are not linear in the velocities.
These came back from a search.
Shut up. Okay, so, and then times, this is x double dot j, and this is lambda k equals, so that's the first equation, and then on the right hand side I have my applied forces at the center of mass, and then I put my constraints on the acceleration, so s kj, and here we have a lot of zeros, kk, as many as kk, and then minus s k j comma I x dot j x dot I, and the order doesn't matter here so much. So these are the equations of motion now, and of course they have a very strong similarity with the holonomic constraint equations. But note that there's no comma here. This is just a matrix, a linear mapping. It's not a differential of something. So how does it go? We solve now for x double dot j, and we get for free lambda k, for free, sort of. Then we do a numerical integration step. And it goes like this, like the next position is the previous one plus, yeah, I always write this like numerical x dot n dt, and the new velocity is the old velocity plus numerical x double dot n dt. This can be some Runge-Kutta scheme or whatever. But note, of course, that we get new coordinates. So the new coordinates, x n plus 1. Well, they are okay. They are okay because we have no constraints. We have no constraints on the xi's. But then the new velocities, oh, why does it drop out? Okay, quit. Air server. Yeah. I have to kill this guy. Okay, that is killed already. I have to start it. It says okay. Well, don't trust it. Yeah. Okay, we go back to this guy. I don't like these interruptions. Where was I? So the new velocities. x dot n are an approximation, right? And we have to make sure that they fulfill the constraints. So we have to raise the question, do they fulfill the constraints? And in general, they don't. In general, they don't. So we can check that, and let's put a slur here. So like the approximations, and here a slur for the approximations for these guys. So we have to check that. So we do ski times x dot slurred n plus 1, and then we raise the question, is it 0? If not, and usually it's not, of course, then of course we need to do, then we need a one-step Gauss-Newton process. Oh, that's a Gauss-Newton process. Right, so we say, well, the real velocities are these approximate velocities, right? Plus some increment, delta x dot I. Then, of course, we have the constraint ski x dot I should be 0, or in other words, we get ski x dot slurred plus ski delta x dot is 0, or in other words, we can try and solve our delta x dot I is minus ski with a plus. Remember, this was the more or less inverse, or the more Penrose inverse, times this ski x dot slurred I, the error in the thing. And then with this one step, we have updated our coordinates. Okay, so that is in a nutshell how we are going to do the constrained, non-holonomic constraint system. Of course, if you have also regular constraint, holonomic constraint, then it's a combination of those two, and you get as many multipliers as you also have holonomic constraints. And again, you have to then do the Gauss-Newton process first for the holonomic constraints, and then you differentiate them and you add the non-holonomic constraints, and you do the Gauss-Newton process one step for those. Which is actually the homework problem of this week. But let's do an example to show how this all happens. And I also have coded the example in MATLAB, so we can play a little bit around with it. And the example I want to talk about this afternoon is the Chaplygin sleigh. And it's a famous thing. And as I already said, this rolling contact with no side slip is the same as a skate or as a sledge or a sleigh. Well, why is it called the Chaplygin sleigh? Who was Mr. Chaplygin? Well, there was a guy called Sergei Chaplygin, and I always pronounce it wrong, of course. My Russian is not so fluent. 1869 until 1942. 1942, and you can imagine why he died, I guess. Anyway, he was from Russia. And he was a mathematician and a dynamicist, of course. He was very interested in dynamics of mechanical systems, but a very mathematical approach, like most Russians do. Actually, the whole dynamics of non-holonomic systems really flourished in Russia, because of this mathematical approach also to the problem. Back to Sergei Chaplygin, what was so special about it? Well, his teacher, his teacher was Sadov, and who is Sadov? Yeah, Sadov is famous because he designed the Sputnik. So he was the designer of this Sputnik, and then some of you may think, what is Sputnik? Well, Sputnik was this first satellite, which was out in space, and which was sending this beep, beep, beep electronic signal and for which started actually the whole NASA program of man on the moon and all, man in space and all those kind of things, the whole race. Because the Americans were scared to death that the Russians would beat them in the space age. Anyway, so Sadov, designer Sputnik, the teacher of Chaplygin interested in mathematics, dynamics and non-holonomic dynamics. Now what is the Chaplygin sleigh? Well, that's one rigid body, so this rigid body. It has a center of mass somewhere, so let's say here. And then it also has a skate, and I make it a little simpler than the general one, because in the general case the skate can be here, but well, without loss of generality for now, I say, well, let's put the skate here. I don't put the skate, of course, at the center of mass. I put it a little bit off the center of mass. Okay, so the skate is in A. This is the CM. Yeah. What else? Oh, so there is apparently a distance between the distance A. Yeah, and then of course at the center of mass we have a mass and an inertia. Of course the body has an X, Y and an orientation, right? It's one rigid body where the orientation is defined as this angle, of course, phi. Of course I need a coordinate system. Thank you, Heike. X, Y and phi being positive like this. So this is my inertial system. And again, then we can say, well, what? So this is the skate, right? So only skate here. So point A only has the opportunity to have a velocity in this direction and no perpendicular one. But to write that down, we have to write in general down that there's a velocity here at point A, right? And then we have to decompose that velocity into two parts, and then especially of this part of the velocity, that is this V A perpendicular, we have to say that should be 0. So the V A perpendicular should be 0, and that is our non-holonomic constraint. Yeah. As coordinates, of course, we have it's one rigid body, X, Y, and phi. Now, before we do any derivation, the mobility. What is the mobility? And I would always say, well, the mobility is about possible velocities, how you can move, velocities. And in this case, because we have one non-holonomic constraint and 3 coordinates, apparently this mobility is 3 minus 1 is 2. Oops. So the velocity mobility is 2. And that's a bit strange, but maybe you can also compare it to a car, or I mean a car, as long as the wheels stay on the road, you can put a car anywhere in space. If this is the car and this is the plane, then you can move around over the plane and you can put the car in any direction. However, the car has wheels and it can only move in this preferred direction, right? And it cannot just move sideways. Therefore, you have to do a complex thing like parallel parking to get into a parking spot. You cannot get into it in some strange way, or you drive by and you do like this. No, you cannot do that. So that's what we mean by mobility. So although in the coordinate space you can have every configuration, every x, y, phi, in the velocity space you lose one way of mobility, and with a car it's pure sideways, and with the skate in the middle. Okay. So let's derive the equations of motion for this. We have to define, of course, our constraint on the non-holonomic constraint in terms of these coordinates and their speeds. So, so the skate in A tells us that VA perpendicular is 0. And we can write this VA perpendicular as being like the dot product of this velocity in A with some direction vector, E perpendicular, right, which is this vector. And the V in A is, we only know these guys, so that's a bit tricky. We come back to that in a moment. And the E perpendicular, that's easy. If we look at the orientation of the body, then that is a minus sine phi, cosine phi, and that's it, right? And yeah. Now, what is the position velocity of point A? Well, if I use the transport theorem, very elegant word, I could say, oh, that's the velocity of the CM plus omega cross the distance of A with respect to the CM. And if I do that, I really, because I use the cross product, I really have to go three-dimensional, but you can also think, oh yeah, three-dimensional, then everything is in this Z0 plane, so I put a 0 here. The only thing which is not in the plane is, of course, the rotation, because the rotation vector is in the Z direction. It's the omega about that, or phi dot about that Z. Okay, so then we get to derive this vector, we need a VCM. That's very simple. That's just x dot, y dot, and 0. Then we need the omega vector. That's also simple because it's perpendicular to the plane, so that's a 0, 0, and a phi dot. And then we need the distance from A with respect to the CM. That's a bit more tricky because we have this distance A, and I should make actually a unidirectional thing out of that. Yeah. So it's the backwards position from the CM. So what is that? So that's a minus A times cosine phi, right? And that's a minus A times sine phi, and that's a 0. Okie-doke, so now I have all the ingredients, I have the formula, and I can calculate what is the velocity of point A. So x dot, y dot, 0 dot plus 0, 0, phi dot, cross product with minus A cosine phi minus A sine phi 0. And the outcome of this velocity, V dot, is, x dot, a cross product, minus minus becomes plus, right? Yeah, A times phi dot sine phi. And the second one is y dot minus A phi dot cosine phi. And the last one is hopefully 0, right? Okay. Now finally, to find our condition, our V A perpendicular is 0, we have to take this V dot A with this E perpendicular, and that is, well, let's write it out, that's okay. X dot plus A phi dot sine phi, Y dot minus A phi dot cosine phi 0, and a dot with the minus sine phi cosine phi 0 equals, so that's VA perpendicular equals minus x dot sine phi, that's the first, minus A phi dot sine squared phi plus y dot cosine phi, yeah. Minus A phi dot cosine squared phi. Yeah, it's a sub phi, it's not so nice. And 0 times 0 is 0, so it should be 0. Of course, we see sine square and cosine square, so we get the VA perpendicular is minus x dot sine phi plus y dot cosine phi minus A phi dot, and that should be 0. So this is our non-holonomic constraint, right? Or in other words, we learn to give that a name. We call it then S equals, or S1, but we only have one. So we get minus x dot sine phi plus y dot cosine phi minus a phi dot. Now in the equation of motion we need of course an expression for our acceleration constraint, so we do s dot. Well, again, the same Jacobian, my x double dot sine phi plus y double dot cosine phi minus a phi double dot plus, and now we get our convective terms. Let's put a bracket around it. Minus x dot cosine phi phi dot. Then the second one is minus x dot phi dot sine phi, and that's it. Yep. Okay. So now we can form the equation of motion, but before we do that we maybe should check this result, right? So the velocity is this projection of the velocity plus a distance times phi dot, and that's of course correct. If we have here a speed x dot y dot, then the speed here is this speed, which we project on this and this direction. We only need this one, but speed can be have a general direction. And then of course if the thing is rotating, then we have the rotational speed times this a gives also a lateral velocity, omega dot r, or in this case phi dot times a, and that's in that direction, that's opposite to the VA perpendicular, so that's a minus sign. So I'm happy with the expression. I think this is correct. The feeling it's correct. Okay, then the DAE, which we finally can form now, is our constrained differential equation of motion. Yeah, let's see if I have enough room here. Yeah, so we have a mass, and an inertia, and then we have only one constraint, right? So it looks something like this. Do I need enough space? Yeah, that's good. So mass times acceleration, and the acceleration is x double dot phi double y double dot phi double dot. Then we have only one Lagrangian multiplier, lambda. That is the force in the perpendicular to the skate, of course. Then equals, so let's form first the equation of motion. Mass times acceleration equals the applied force, Fx, Fy, and the torque, which you apply. So that's all at the COM, at the CM, of course. Then we need, of course, here the Jacobian of this guy. Now what is the Jacobian of this constraint? So with respect to x we get minus sine phi. With respect to y we get cosine phi. And we do have a component with phi now. But it's still non-holonomic. You can check that. If you take again derivative, the mixed derivatives, you will see it doesn't work out. So it is really non-holonomic. So with phi double dot, so that's a minus a here. Of course we have all zeros here. And then we just write the constraint equation here, minus sine phi. It's a cosine phi and a minus a here. And then on the right hand side this with a minus sign. So maybe for clarity I do double minus x dot phi dot cosine phi, that was not so clear, minus x dot, no, y dot. Ah, I spotted an error. Haha, that's cool. This guy should be a y dot, of course. Yeah, and then we go to this guy. And we also make a y dot out of that. Go away. So, yeah, y dot, phi dot, and that is sine phi. And these are actually our constraint equations of motion. And, of course, we have to add some glue. Yeah, we have this is this new brand of glue, a Holo glue. Remember? No, it has a bit of a different color, different taste maybe. Huh? Don't eat glue, actually. It's not good. Not good for you. Don't sniff it also. Whatever. And of course we have to make sure that the velocities stay on the surface. So we have minus x dot sine phi plus y dot cosine phi minus a phi dot is 0. This constraint equation which we're going to use when we want to stay on the constraint surface. Okay, so that was a long derivation for a, well, seemingly simple problem. Yeah, I like to now move on, and I want to do a simulation of this case where I have my system, and this is the system I'm going to do. So I have a center of mass here, and I have a skate here, and the distance here which I took was 4. It's all in standard units, 4. I took a mass of 1 and a mass moment of inertia of 0.1. It's yeah, I don't know why I took these numbers. Anyway, then I'm going to apply a force, just some force at the center of mass, and I'm going to put a little bit drag here. I'm going to put a drag force here, because if you apply a force, then the thing will accelerate, and well, that's not so nice for the simulation. I see there is a question in the chat. Sven or Stephen, I will not come back to that now, but after the lecture, in a quarter of an hour, we have a Zoom meeting, and I will give the Zoom address. That's my personal Zoom address, and everybody can join, and then we can discuss any issues which are there. Okay, so this is the problem: some applied force, some mass, some inertia. The skate is this is a 4 from the center of mass. Then the drag force here, as I said, is a minus 1/2 times the velocity in this direction, and not the lateral one, because there is no velocity, of course. This is the drag force, like dragging your skate. And then there will be, after a while, when I apply a force, there will be some equilibrium and it will go into some direction. But the interesting thing is, of course, in which direction will it move and how will it move? Because this thing cannot move sideways. As I said, it will make strange maneuvers to come into some direction. You would think, if I push in some direction, it will move in that direction. Well, initially it will not, because due to this skate thing. Like with a car, you want to move sideways, you cannot, you have to do parallel parking thing. Okay, I have implemented the thing. We can get rid of this thing now. I don't kill it, I make it small. I go to MATLAB. Yeah, and apparently there is also a PDF file with a derivation. I will get that in the other picture, but yeah, oh, that's a bit too quick. So this is actually the, where are you? I lost something. Come back. Here. Yeah. So this is the derivation sheet, but it's actually exactly the same which I did now on the iPad. So exactly the same, exactly small a, capital A, but for the rest it's the same. Now we have to implement this, and the implementation is here. So this is the main file running the Chaplin sleigh. Of course, the backbone of the thing is, of course, the differential equation. So let's look at the ODE of the sledge. Yeah. So here we have this thing. It's ODE DAE. It's a mixture thing of the of the Zeppelin sled. I use global variables. You should never do that, but for now it was quick and dirty. I have position, I have velocity, I have a mass matrix, I have my non-holonomic constraint, so we have to open that up, right? I can do that, yeah, open. Which is just a vector coming in, and then the outcome is the constraint value, the Jacobian and the convective terms. So again, I copy them in reasonable variables. Here you see minus sine phi, cosine phi, and minus a. I evaluate it with the current velocities, and these are these convective terms with the minus sign, right? So that is the constraint. Then with the constraint and the here we see we have after lecture question and answer on Zoom in 10 minutes. Okay, thank you for reminding. Then I form the DAE, I solve that, and I return, of course, only the time derivatives. We're not interested now in the forces. I store them secretly in some global variable. So that is a differential equation. Then the engine running it is this guy, of course. Just the simulation of the motion is in a loop. Just call for the DAE. And the most important part, of course, is after one step of numerical integration, we have to get the speeds back on the surface. So we have to check the speeds, and that is an important part. That's the one-step Gauss-Newton process. So we take the constraint, we come with the predicted values, we take the constraint, we get the value and the semi-Jacobian. We do this more Penrose inverse thing, and then we correct that, and we have the in a one step the correct speed. So then I have corrected the speed, and then I can rerun this loop and continue. Now the initial conditions are important, of course. As I said, it's a distance of 4, the skate 4 from the center of mass. The mass is 1, mass of inertia 0.1. There's a drag coefficient to get some equilibrium. And for now, I'm just pushing the sled forward and sideward. And it has no initial velocity or whatsoever. So the sledge is just in the origin, oriented along the x-axis, and I'm just starting to push in the longitudinal and in the lateral direction. And you would think, oh yeah, then a normal thing would just move directly in that direction, 1, 1. But as you will see here, this will go differently. So how does it move? It starts here, and then it takes some time to get on this 1, 1, 1 track. So eventually, of course, it will move in the direction by which I'm pushing. It's 1 over 1. But it takes some time because of this go back. Ooh. Because of this non-holonomic constraint, because this point cannot move sideways, and it needs some parallel parking type of maneuver. Now it's interesting to look at other results, like for instance the angle of the so that was the path, the path of the CM and A, which we saw already here. Then here we see as a figure, we see the orientation of the sled. So as you see, the orientation takes some time to start changing, and then it comes at it does some overshoot, and then it comes back at finally pi over pi over 2. Then the following figure is the speeds. So, and that's interesting to see that there is an equilibrium speed apparently. I apply a force of 1 and 1, and there's a resistance of 1/2, so the speed in both directions should be 2, and that's eventually the speed we reach. There's some overshoot in the lateral direction, and that's it, to get this orientation. And of course, and then of course the x also comes to, oh, there's a small overshoot. Cool. And you see the change in the orientation. I also stored the constraint force, the lateral force at the skate, and then you clearly see, oh yeah, in the beginning there is a force. So I'm pushing sideways, but it's reacting against me. And then after a while, the force is in the direction of the motion, and there is no constraint force anymore. I will put this example on the web. It's sort of funny to do all kind of other initial conditions. Funny if you're interested, of course. Now let's say we start with some initial speed, and let's say we give it some forward speed, so it was x, y, and phi, and then x dot phi, y dot phi dot. So let's say we give it just an initial forward speed, and we just and we're going to push it only sideways. So initially it will move, go away. Initially it will move forward, but the force is pushing it sideways. So in the end it should go sideways. So let's see. Yeah, and there we go. You see? Oops. And it takes some room to do that, to go in that direction, because of that skate here, right? Again, we can look at constraint forces, we can look at the speeds that we reach, the same here, also 2 because of the resistance and the angle. But you could also say, well, why not start with some initial velocity and no forces, and let's see then what happens, right? So we start with initial velocity forward, and we take some rotational velocity, let's say also 1. I don't know, I have no clue of units at the moment, so and let's put the drag to 0, so there are no losses. So the thing starts moving, and then it will move in some way. So what will happen? Nothing much, right? There's not much rotation going on. So maybe we should add a little bit more rotation. So the rotational speed should be a bit higher, say 10. Okay, what happens? Oh, go away. Ooh, this is very strange. Let's do that again. That is not correct. Oh, let's do that again. So what do we see? I see nothing. I did something wrong. Oh, I don't want to debug. Run. Oh! There's a strange initial step in the beginning. And I think I know why. Looking at the figures, we see constraint force making a sharp jump, speeds making sharp jumps, angles making sharp jumps, and I think I know what is going on. I still have 3 minutes, yeah. I think that the initial velocities do not fulfill the constraints. That could be the case, right? So maybe we should check this, and we can check it because we can calculate what are the constraint values. So we just and then we stop here. We only run the first part. So on y0, let's check what our constraint value is for the initial speeds. So we only run this section. Aha! It's not 0, it's minus 40. So meaning that these velocities do not fulfill our non-holonomic constraint. And that's of course super clear, because if we look, now I need a tablet. Come back to me. Yes. If we have this body here, and we have the skate here at 4, and we have the center of mass here, and we start here with a forward velocity of 1, and we take an angular velocity of 10, then since this can have no zero velocity, then the initial velocity here should be 10 times 4, right? This distance is 4 in the upward direction, so being 40. And if we do that, then the velocity here is 0, and these should be correct initial values. So let's check that. Air server, yeah, okay, so good. So now we say, oh, then this should be 40. Let's run this section again. Yeah, S is now 0, right? We have so this should run, and then we advance, and then we run that section. We advance and we run that section. And then what do we see? Yeah, that's a bit high value at the 10. There was a inheritance of my not understanding. So let's make it 1 again, and let's make it 4. And let's run the whole thing again. Yeah, and then apparently after a while it goes into some direction. So it has an initial forward speed, it has an angular speed, and then it goes into some direction. And it's sort of fun to see, hey, this direction, the final direction, where does it depend on? This final angle. Maybe if we change the speed, if we make the speed, if we halve the speed, so 0.5, and this is becoming 2, then let's run it again, and my expectation is that the angle will be a little bit less. Yeah. And of course you can try and find an expression for what is the value of this final angle. What is the angle? It's this graph. The angle with respect to the horizontal as a function of the initial speeds. Also in this assignment. I don't know the answer, by the way. And you see the constraint force is 0. There's no lateral force anymore. And why is it changing direction? Well, because there's a constraint force. And because there's a force, there's a motion, right? But the force is not doing any work. Okay, I will put all this stuff on Brightspace, and if you're interested, you can play around. Now we go to our, I stop this, and we go to our Zoom question and after lecture question and answers. For those who do not know what the address is, this is the address. So I will stay there until 4 o'clock. It's TU Delft Zoom, us, my, Arend Schwab. If you have no time to write it down, no problem. It is on Brightspace. Go to Brightspace, look at the announcement, and the address is there. So I'm going to start it up now. And come open my Zoom. Yeah. Jan Willem is already there, very nice. Okay, and then I will stop the recording here and I will stop the streaming. Stop the